My pleasure to introduce our next speaker from the Grad School of Education at UC Berkeley, Kiera Chase. And she is studying how educational technologies contribute to perhaps our willingness to accept transparency and privacy losses. So maybe we're training ourselves to be more complacent than we should be. And what technologies can enhance and disrupt these kinds of dynamics. Please help me welcome Kiera Chase.
Thanks. I'm not used to this whole mic thing. I'm just used to standing in front of a classroom. So, sorry. As Greg said, I'm Kiera Chase. I'm a BCNM DE PhD candidate. That's a lot of letters. And I hail from the School of Education, where I study with Thor Abramson. And the title of my paper is When Less Equals More, looking at transparency in learning. So, as you know, this conference is bringing together a wide variety of stakeholders from so many different fields that are examining this concept of transparency and how, if, when, or why we should manufacture transparency. As an educator, this discussion is particularly urgent because what might be transparent to a teacher may not be transparent to a student, or what might be transparent to a student may not be transparent to another student. And in fact, the process of actually making a particular concept transparent is what I will argue really essential to what we call learning. So I Googled transparency. It's an adjective, and it means something that lets light pass through it so that you can see what's behind it, something that's easy to perceive or detect, and in the case of computers or software, operating so that the processes are not perceived by the users. So here we already see a little bit of clash between how these things can be interpreted. I hope I'm not the fourth person to have done this today. In education, when we talk about transparency, we talk about it in the following ways. A necessary function of an artifact, in most cases we're talking about an educational artifact, will become transparent to the student when they recognize that particular function as having an affordance towards solving a particular problem. So being able to see through the behavior of an artifact to what lies behind it is an educational opportunity. Because most of my research is in math education, I'm going to be using a lot of math examples today. Don't worry, my mathy examples will be totally transparent, I promise. But before I get into the math part of this, my father is an architect, and when I was growing up, there was a lot of stuff like this laying around his drafting table in his office. And I remember kind of, looking at these things and thinking about each tool. And, the brush, it seemed pretty obvious what you would use the brush for. And the straight edges, that I could make sense of. But I was particularly curious about this object. For a long time, I didn't know what to make of it. I wasn't sure how you hold it. I wasn't sure what purpose it served. I was pretty sure that it drew something because there was a pencil in it. Then I saw him use it, and then I used it, and at this point, I realized the function that it served. I realized that, of course, it made a great circle because one arm stayed in one place, and the other arm went around it, and that they were kept at a particular distance, at the same distance. So in that moment, I had essentially uncovered the concept of radius without any formal education, just by seeing through the artifact's function to the embedded mathematical rule. So I'm going to show a kind of a totally different example. I apologize in advance for the YouTube film quality.
6 into 4
2, 6,
minus 1478.
1138.
1138 minus 547. 591 minus 358
2333.
minus 199. plus 36 plus 58 plus 74, 74, 85, 96, 63, 21.
5541.
Minus 247.
298.
So quick show of hands. Who's seen this before? It is creepy. Nobody? Wow. I think it's fascinating that these students can perform those types of mathematical calculations with that kind of speed. I mean, it blows my mind. I'm also really fascinated by the strategy that they're using. I don't totally understand it. I've Googled it, and I'm trying to learn it, but I've definitely not mastered it. But they have. So this system of finger movements that they're doing, it's called like finger abacus, and the corresponding sort of number relations and how it all works is completely transparent to them. So the structures that they were taught serve a particular function of performing these abacus-like calculations. The finger movements are not necessarily an external tool, but it's still a set of structures that serve a particular educational function. So the relationship between structure and function is transparent to these students. Like, talking a lot about the relationship between structures and functions today. So thinking about some of the artifacts that I, or perhaps you, have interacted with to perform similar calculations, let's compare the calculator and the abacus. And here we see sort of a black box versus glass box example along certain dimensions. The calculator obscures the structural properties by which it makes its calculations. The user can't see what it's doing. Whereas the abacus renders these structural properties highly salient and tangible to the user. So the principle of transparency is important to me as an educational designer because if I want students to understand and see the structure and function of a system or a model so that they can learn it, I believe that they must actually build it. So how do we design educational tools so that students can do this? So as an example, I'm going to introduce a research study, Martin and Schwartz, 2005. It's kind of old, but seminal. So these two were investigating how students use particular objects to learn. And they're sort of building on a theoretical perspective of distributed cognition. They recognized that it was very natural and useful for students to use artifacts in the learning process. So many of you may be familiar with these. These are pie-shaped pieces are used to teach fractions. So the idea is that these artifacts instantiate the part-whole relationship, making it more clear to the learner. To create a comparison, Martin and Schwartz used these square-shaped tiles with half of the participants and had them perform the similar tasks. So I want you to take a few seconds and turn to the person sitting next to you or near you, partner up, and thinking about these two different sets of manipulatives, talk about the following question. Which set of manipulatives were more effective and why? Okay, finish up your last thoughts. In 5, 4, 3, 2, 1, 0. Craig, can you please stop talking? Do I have one or two brave souls who'd like to share really quickly what they talked about with their partner? What?
I was going to take it on myself. My reason why.
Oh, you were thinking about it on your own?
Yeah.
Great. What did you and you have to say about it?
So I think the first one was the more effective one because it actually shows you what you're missing.
The first one being
Circles of pi.
the pie shaped. Okay.
Because you visualize what is missing, what fraction, what. Well, the other one, even if you put squares, you didn't know what the unit was. So.
It's true. Yeah. This is exact. Very good point. You can visualize what's missing. Anybody else have a different thought? Anyone else's partner have a different thought? Yeah, in the back.
So I speculated that the tablets have a virtue of enabling you to deal with larger numbers in a way that the segmentations beyond 6, you just couldn't hold that easily.
Oops. What do you mean segmentations beyond 6? You mean like...
So the bottom 3, I no longer know easily can calculate, if you would. It pulled in my head how many parts there are.
Right.
But in a linear sequence of tablets, I wouldn't have that difficulty.
Okay, so there's like increased retention capabilities of the tiles.
From seeing them in sets played out in 5s, 10s, 20s.
Right. Interesting. Yeah. Both very good ideas. So the results were kind of interesting of their study. The students who used the pie-shaped manipulatives were able to use these manipulatives to complete specific problems that related to the design. For example, like using this top set to share or regroup 5. So the structure of these pieces created a sense of whole. The whole was built in. But somehow, these students did not necessarily recognize this function as an affordance when solving problems. Whereas the students who were given these square tiles could reappropriate the pieces in more flexible ways and performed better on a variety of tasks. And the researchers concluded that this was because the whole is cognitively constructed by the student. So for example, this could represent a half if the student was visualizing this as the whole. Or this could represent 3/4 if the student was thinking of this as the whole. So the functionality that these pieces perform is actually created by the student. So in another example, Mira wished to develop a set of tools that would enable students to understand mathematically functional relationships, so that this relationship between given a certain input, there's a determined output. So some students were given a system that looked a little bit like this. So given an input, i.e. when you turn that crank at the top one time, there would be 2 different outputs. That the black and the white balls would be at 2 different places as measured by the numbers on the side. And if they could try this over multiple times, that they would be able to determine the relationship between one input and the black and the white balls. And if we examine the structure, we can literally see that the spools at the top of this device are different sizes. And so given one input, the white side and the left side are going to move up and down at different rates. So some students used this, and some students used a computer program where they simply typed in an input and the computer generated an output. For example, given an input of 1, on the black side the output would be 12, and on the white side the output would be 8. So again, the results were not as anticipated. So Mira had anticipated that because the structure of the device was literally visible and observable to the user, that the function would be transparent to the user. And yet that wasn't necessarily the case, because the participants who were using this computer program developed superior understanding of the mathematically embedded structure as measured by their understanding on various assessments that were looking at their understanding of the relationship between input and output. So Mira concluded, and this is the quote we saw at the beginning, that the necessary function of an artifact becomes transparent when the student recognizes this function as an affordance towards solving a particular problem. So the students who were using the crank device did comment on the size of the spools, but they didn't see this function as central to the overall structure or to help them solving the problem at hand. Whereas the students who were using the computer program immediately recognized that the structure, even though they couldn't see it, and understanding how that structure behaved was integral to solving the problem. So Mira's work concluded that building transparency is actually a subjective process, and as designers, we must learn how to design for this process of building transparency. So with that in mind, I'm going to speed date you with my dissertation. My dissertation focuses on how students use a learning environment called Giant Steps for Algebra to build transparent understanding of algebraic structures. So in this activity, students use the interface to construct diagrams, and through constructing the diagrams, really a minute? Wow. 5 minutes, thanks. Through constructing diagrams, they kind of realize some of the important algebraic rules. So here we see that a student has constructed a diagram for the story that is on day 1, a giant walks 4 giant steps, as represented here on the top, and the giant buried a treasure. And then on the second day, the giant goes 3 giant steps, and then goes 2 meters more and finds the treasure. And so what the student can interpret from this drawing is that the final giant step is equivalent to 2 meters, and that perhaps they can assume that then all giant steps are 2 meters, and then the treasure is buried 4 meters from the start. Yay, find the treasure. So in level 1, students used the modeling tools to construct the story that I just explained. And as you can see, there's certain inconsistencies that occur. They're not receiving any support necessarily from the computer program to construct the size of a meter or the size of a giant step. And they have to assume that this consistency. I'm trying to go fast. So in level 2, once students have had some time to play around with it and articulated the importance of actually having a consistent unit, i.e. a consistent meter, then the computer program actually introduces that control and automates the meter for them. At this point, the student then only needs to focus on adjusting the size of the giant step so as to achieve parity with the story, with the narrative. And in this case, the student actually has to make quite a lot of adjustments until they actually achieve fidelity and then find the answer to the story. And then finally, in level 3, the student is granted yet another automation, and now the giant step and the meters are all created uniformly, yet because the giant steps, you still need to determine the size of a giant step because it's the variable, they all auto stretch and shrink so that the student only needs to focus on achieving fidelity with the story and then calculating the distance. So the results of my research indicate that students who work with the gradual automation outperform students who receive full automation from the beginning, as measured by significantly higher outputs on transfer tasks that measure transparency. So we conclude that students need not be spoon-fed ready-made solution strategies for mathematical problems that they first encounter, and that they can actually reinvent mathematical knowledge by building these structures. In particular, students develop subjective transparency of mathematical concepts by creating, articulating, and generalizing the structural properties of the models that they use to solve particular problems. And to understand these systems, they must build it. Thank you.
Wow, thank you. You made me think pretty hard about giants and steps.
Awesome.
Those are really interesting concepts, and it seems to suggest that the more friction we put into the process of learning, the deeper the learning gets. Fascinating. Any questions for Kiera Chase?
I think there's a healthy balance between this idea of friction, how much friction, and how much ease. If there's too much friction, then kids get overwhelmed and they shut down.
Yeah.
So it has to be an accessible amount of friction.
And it has to go away when they actually understand it.
Exactly. Yeah, they have to not be burdened by having to continue to reproduce meters over and over again with a glitchy computer program. Like once they
Yep.
figured out, okay, my meters need to be the same, then bam, they get it.
So you want the friction exactly the right place. Well, thank you very much.